Okay, so we will discuss about that also. So okay, now you can start. So we are discussing about the Milky Way, and the Milky Way that is our galaxy. It is also known as Mandakini. It was originated 12 billion years after the first event. First event means the Big Bang. The Big Bang, the biggest explosion of the universe. So in that explosion, the matter was thrown outward, and slowly the temperature that comes down, that was reduced. And 12 billion years after that, this spiral galaxy was formed. In the galaxy, we have around 100 millions of stars. Now the question is that how the star is formed, how the star is originated in a galaxy. So if we go back to the Big Bang, so in the Big Bang, space and time was formed, the energy and matter was originated, isolated electron, isolated proton, isolated neutron, and isolated neutrinos were formed. And finally they assembled to form the matter, and then finally to the galaxy, right? So now the question is that how a star is formed. So let us see the geometry of the galaxy. So if you see, this is the outer arm of the galaxy, right? Outer ring of the galaxy, or you can say outer arm of the galaxy. Then it is the second inner arm, then first, and then if you see, we have the central part. The central part of the galaxy, that is known as Sagittarius, and the outermost arm of the galaxy, that is known as Orion, outer part of the galaxy. So now in the outer part of the galaxy, due to lot of hydrogen and lot of dust, we have a cloud, a big cloud of hydrogen and dust, and that big cloud is known as nebula. And the cloud is spinning, the cloud is rotating. So this is a rotating cloud known as nebula. So now there is some physics how a nebula turns into an amaryllis star or a protostar, right? So a big chunk of hydrogen and dust particles, they are rotating, and because it's a big chunk, so now the physics comes into the picture, the gravity that comes into the picture. So now you can say this is the birth of the gravity, the birth of the gravitational force, the birth of the gravitational field. Now the first time the gravitational field that started in that point-sized object, right, and then that was exploded due to the infinite gravity. This is the second time. This is the second time when the gravity is creating something new from a cluster of hydrogen and dust, which is nebula, right? Now it will create a new object, or a new object which is a star. So how that will happen? Now the gravity is the inward force, so the gravity will try to shrink this nebula, and the nebula that will reduce in size. When it reduces in size, so physics says that the rotational speed that should increase, right? If something shrink, if you open your arms, suppose you are revolving, you are doing rotational motion on a chair. If you open your arms, your rotational speed will decrease. And if you shrink your arms, right, then your rotational speed that will increase. Same thing happens with the nebula, right? So nebula when shrink due to the intergravitational forces, so its rotational speed that increases, right? So now the rotational speed increases, and the hydrogen that changes into the helium, right? So when hydrogen changes into the helium, then another physics originated. Hydrogen is lighter, helium is heavy. So this is the same situation when we fire a bullet from a gun. The bullet is lighter, right, and the gun is heavier. So the gun that do recoil, right? So when the gun do recoil, it will go towards the center, right, and the bullet will go outward. So same thing happens with the hydrogen and helium. When the hydrogen changes into the helium, so the helium is heavy, that goes towards the center, right? So when it goes towards the center of this star, and the hydrogen that go away. So when hydrogen that goes away, so there is a force which is throwing the hydrogen outward. That force is known as the centrifugal force, right? So the centrifugal force that throw the hydrogen outward, and helium is thrown inward due to the gravitational force. So now in this star, which is known as the Ambrose star, or a protostar. In this protostar, hydrogen is thrown outward, helium is thrown inward. Hydrogen is thrown outward due to the centrifugal force, and helium is thrown inward due to the gravitational force. So now the new ball star is there, right? So now this new ball star, which is throwing hydrogen outward, helium inward, right? So this will start moving clockwise. The galaxy is moving anti-clockwise, right? The galaxy is moving anti-clockwise. The arc of the galaxy, the origin of the galaxy is moving anti-clockwise, but the journey of the star that goes clockwise, right? With respect to the galaxy, that is clockwise, right? With respect to the galaxy. So now this star, right? This star will move this side. Now, if you see Wikipedia, right, then you will find from embryo star final to the stable star, right? It will take around 5 billion years. 5 billion years. But this is not an accurate value, because how much time embryo star take to become a stable star, that also depends how much mass it has during the birth, right? During the birth. If the mass is heavy, right, or mass is less during the birth, so this time may change. So we will just take a rough value. Yes?
If the mass is here, will it take longer?
If the mass is heavier, definitely it will take longer. It will take longer, right? So now stable star means the outward centrifugal force on the hydrogen and the inward gravitational force on the helium. They balance each other. So when the two forces they balance each other, that stage of the star is known as stable star. Now we don't have the information for how long the star will be stable. Right? This may be for 1 day or for 1 billion years, no information. Right? So only just we know the star is a stable star when the outward centrifugal force on the hydrogen that is completely balanced by the inward gravitational force on the helium. Now again the star, again just go to the, this star is trying to fall in the center. Right? This star is trying to die. Right? Now it's moving in the first arm. This is origin, right? First arm. So from the embryo star to the stable star, this is happening in the first arm. Now from the first arm, finally it will go to the second arm. Now when it shifts to the second arm, right? Second arm, second inner arm. So that stage is known as red giant star, and in this red giant star, helium core becomes so heavy, right? Because helium atoms, they are heavier than the hydrogen. So helium core becomes so heavy compared to the outer layer of hydrogen. So now there is one more process happening, because this star is moving to the inner part, right? So when something moves towards the center, again its rotational speed increases. When its rotational speed increases, so star has a different layer of hydrogen. So it means when rotational speed of that red giant star increases while shifting from the outer arm to the inner arm, so due to the difference in the speed of various layers of hydrogen, there is a intermutual friction between the layers, right? Inner layer of the hydrogen, they are moving faster as compared to the outer layer. You getting my point? Right? The inner layer, if we say the center part is the helium, and around that helium, hydrogen is revolving in the form of layers. So there are different layers of hydrogen. So physics says that the inner layer, which is close, like we say the electrons which are close to the nucleus, they are moving faster as compared to the outer electron. The same thing happens in the astronomy also. The inner layer of hydrogen, they are moving faster as compared to the outer layer. So due to the mismatch in the speed of the inner and the outer hydrogen layers, there is a friction. You are getting my point? Inner layer is moving faster, outer layer is moving slow. So that creates a friction. Due to that friction, the outer layer of the hydrogen, they blast. How the outer layer of the hydrogen, they blast due to the friction. Inner layer around the central helium, they are moving faster as compared to the outer layer. So there is a mismatch in the speed, rotational speed of the outer layer. So that creates a friction. In that friction produces such a high temperature that makes a blast, and that blast is known as supernova explosion. Right? And in this supernova explosion, tremendous amount of heat and light is emitted. The light that spreads to the every part of the galaxy, right? So the light will spread to the every part of the galaxies, up to the Orion also, right? Up to the outer arm also. It will go to the inner part also. So our sun, right? Our sun, our solar system, this is our galaxy. So the galaxy was formed 12 billion, and our solar system was formed 10.5 million after the means the life of our solar system is 10.5 billion years after the first year, right? Galaxy is 12 billion and our solar system is 10.5 billion. Already from here to here, 6 million years are gone. From here to here, another 2 million. So 8 million years are already gone. The total is 12 million. So the leftover lifespan of the sun is, our sun is just 4 million. Remaining life of our sun is 4 million. So our sun right now, it's a red giant sun. It is in this state. Now it's in the second arm of the galaxy. Our sun is in the second arm of the galaxy. Right? And from here, right, it will move to the black hole. Right? Finally, slowly, it will pull the accretion disk of the sun. You getting my point? The accretion disk is the boundary of the sun. Boundary of the sun that is filled with the hydrogen. Getting my point? So slowly from here, the hydrogen that will be pulled or that will be attracted by this black hole. Black hole, supermassive object having manifold gravitational force as compared to the sun. So the gravitational pull of the black hole slowly, right? Now from here, the countdown of the sun that starts, right? And the countdown is just 4 billion years. Our life is so small, so the 4 billion for us, that's so big. But for the celestial time, 4 billion is not so big time, right? So all the celestial phenomena, they happens in the billions. I mean, this time, life of a star is in billion, our life is in just, right, 50 or 70 years. So after 4 billion, right, the gravitational pull of the black hole that will engulf the sun, and finally the sun that will die, that will fall into the black hole. So the journey of a star that starts at the outer arm of the galaxy, and finally the star that is engulfed by the black hole. Right? Let us go to the next slide, and the next slide that will decide whether a nebula that becomes a white dwarf, right? So now I started with the nebula, right? So what are the conditions? How a nebula that sometimes it becomes a white dwarf, sometimes it becomes a neutron star, and sometimes it becomes a black hole, right? How a star that, now the question is, from where the black hole came? Actually the black hole also came from a star. Now which star finally become a black hole? If we see the black hole of our galaxy, from where the black hole came? From where it came? Now let us study that part. A star finally turns into a black hole. A star finally turns into. So the present black hole in our galaxy, actually that is the death of some star, right? That is death of some star. Now how a star, already you know the star is born by a nebula, right? The star is born. Now everything is decided by the mass. In astrophysics, what will happen at the end of a star, that is decided by the birth mass of a star. Now the nebula that make a star, right? So if the mass of the embryo star or mass of a protostar right? If the mass of a protostar is small, right, means less hydrogen, less dust particle, they just make a little star, right? So if average mass of a star, so finally the average mass of a star, that will become a red giant, yeah, red giant like our sun, and finally that red giant again that will explode, and that will explode again, that will create a type of nebula which is known as the planetary nebula. So it means that will throw the hydrogen, dust, everything outside it, and finally it will become a white dwarf. So this is also very important question for IGCSE, how a nebula turns into a white dwarf. So means if less hydrogen and less dust that is accumulated, right, in a nebula, and finally that nebula that creates a little star, a less massive star.
So, from planetary nebula to white dwarf, so after a red giant like explodes into a nebula, the core lattice became a white dwarf.
Yeah, the core is the white dwarf.
What does it do? Does it die?
Because rest of the material that is thrown outward, right? Actually, the rest of the material that is hydrogen, right? And the central part is the helium. Okay. Sometime helium changes into the carbon also, right? So the white dwarf, that can be a carbon white dwarf, or that can be a helium, because the hydrogen fuse together at a high temperature to create helium. Helium also fuse together to make the carbon, right? So this can be a carbon star, or this may be a helium star, right? And that depends upon the inner temperature, the fusion process, everything. Now second is, if the nebula is quite big in size, means huge chunk of hydrogen and big chunk of dust particle, they make a massive star. Means the embryo star, that's so massive. So that so massive that will changes into the red supergiant, into the second arm of the galaxy. This also happens in the second arm. Okay, this is originated in the first arm, right? And this is originated in the second arm. And finally, from the second arm, again the outward hydrogen layers, due to their internal friction, huge temperature is created, and that huge temperature that explodes the outer hydrogen layer, and that explosion, the outer hydrogen layer, that is known as supernova. So in the supernova explosion, hydrogen is thrown outward, and the inner part, again, the inner part actually, that is a helium or that is a carbon, right? That is a helium or carbon. So again the supernova, the leftover part, that is the helium or carbon. And now this supernova, this has two options. The supernova has two options, right? Either it can become a neutron star, or it can become a black hole. So again, this is again a very high level discussion. What are the conditions when a supernova that becomes a neutron star, and when a supernova becomes a black hole, right? So let us discuss the conditions. What are the conditions in the last slide? Conditions for a nebula to become a white dwarf, neutron star, and the black hole. So this is the exact mathematics which I am sharing with you, right? And one of the Indian scientist, Chandrasekhar, right? He proposed this data, right? One of the greatest scientists in the astronomy from India, Chandrasekhar. So now, you know nebula, that is a cluster of hydrogen and dust. And if the mass of the embryo star, or you can say if the mass of the nebula, right, that is less than 8 times the mass of our sun, right? The mass of the embryo star, or you can say the mass of the protostar, if that is less than 8 times the mass of our sun, then definitely it will become a white dwarf, right? But if mass of the embryo star, or mass of the protostar, or the mass of the nebula, that is greater than 3 times the mass of our sun, then it will become a neutron star. And if the mass of the nebula or mass of the embryo star or mass of the protostar that is greater than 25 times the mass of our sun, then it changes into a black hole. So the present black hole in our galaxy that was originated in the beginning, that was originated from a very big nebula, and that big nebula or that the very first star, right, the mass of that star that time that was 25 times than the mass of our sun. So this is the condition how some star changes into a black hole. So that is decided by the birth mass of that star, right? If the birth mass of that star is 25 times the mass of the sun, then finally it will die and it will become a black hole. If it is greater than 3 times the mass of our sun during the birth, then it will become a neutron star. And if it is less than, then it will become a white dwarf. Yes.
What is the
Okay.